we were talking about disjoint union find, and in particular we were representing sets using inverted trees. So the idea was that if you want to find the set that an element belongs to, then you're going to just follow this inverted tree up to the root, and then that's going to tell you what set you are in. Okay? The set's name itself is not relevant because we could have decided to call this D instead of H. It doesn't really matter. What we are trying to answer here is whether two elements belong to the same set, right? And then as long as that can be answered, it doesn't really matter what we name each set as. So what we discussed last time was that this inverted tree representation seems like a good representation because you can just find whether two things belong to the same set by just seeing whether they both lead to the same root. That seems like a fairly efficient thing to do. But we also discussed that there can be sequences of operations where you could create a chain of you could invoke a sequence of unions that cause a long chain to be formed, and once that long chain is formed, every time you call a find, you're going to have to end up traversing the whole chain. Therefore, if you have two n operations, n unions followed by n finds, it can easily take n squared time. Okay? So the worst case for executing order of n operations is order of n squared. So we have amortized cost of order of n per operation, right? And what we are going to discuss today is how can we improve this. So now we have seen this, and there is no difference here. So making a set means you make a singleton set with just that element. Find, you're going to keep following the parent pointer, right? Pi is the parent pointer, so you just keep following the parent pointer. And then there is the union, and for the union what you're going to do is, again, given two elements and you want to union the sets they belong to, you have to first find the root of the tree that each of them belong to. That's why Rx equal find x, Ry equal find y, and then we go up and we do the union. Okay? Now, the first technique we are going to use to try to reduce the cost is called union by depth. Okay? So the idea is that instead of allowing these long chains to form, if we try to keep this inverted tree in a sense balanced, okay, so then hopefully you'll be able to build trees whose depths are log n instead of n, right? So that's the basic idea. So what we're going to do is we are going to do the same thing that we did before. We find the root of these two sets, right? We are trying to union x and y. First we find the root of the sets in which x and y are present, and so we call that as Rx and Ry, so root of x, root of y. And if the ranks are same, okay, so what is rank here? At this point, think of the rank as the height of the tree, okay? So there is the root, the set has, the set that x belongs to has a root called Rx. Now you take the height of this inverted tree, okay, so that is what rank is going to be, okay? Now, if the ranks of the two trees are the same, then, well, it doesn't matter which one you make the child of the other, okay? But if one of them has a lower rank than the other, then you're going to make the lower rank one the child, so that your tree will be more balanced that way, right? So if you have so here is a tree here's a tree of depth 2, and here is a tree of depth 1. Okay? So it will be more balanced if you make this the child of this node instead of making this the child of this one, right? So the idea is that you make the one that has lower height or lower rank be the child of the one that has higher rank, right? So that's what this algorithm is doing. You just check that if the rank of X is greater, then you're going to make Y the child. If the ranks are equal, then what's going to happen is that now you're going to end up having increasing the height, right? So for instance, if in this case, if I make this the child, then the rank of this hasn't increased, right? Because this is rank of 1, this is rank of 2, and it hasn't changed. However, if this is also was a rank 2, then now you have a rank 2 child to this node, which means that you have increased the height by 1, so you're going to update the rank. So that's why the last statement, if the ranks are same, then you end up incrementing the rank of the other one, okay? So here's an example, it's just giving you something. So in these pictures, the superscript shows the rank, okay? So when you form a set, initially you do a make set for all of these 7 elements, and when you form a singleton set, obviously the height is 0, and so the rank is 0, okay? And then let's say you do union of A and D, so A becomes the child of D, B becomes a child of E when you do union of BE, union of CF, well, C becomes a child of F, and naturally when you do that, the rank of the root is going to increase from 0 to 1, right? Okay, and then G is still alone. Now, if you do, if you take the union of CG with EA, well, then, no, EB, right? No, okay, I'm sorry, yeah, I'm just getting confused. Okay, so you first do union of C and G, okay, and so you get the tree on the right hand side, okay? So you already had F and G in one set in the previous slide, right? So F and C were in the same set. Now when you take the union with G, then G is going to become a child of F, right? So that's what's happening over there. And then on the left hand side, both AD and EB were in the same set, right? So AD and EB were in the same set. Now if you take the union, again the ranks are same, it doesn't matter which one you make the child of the other, but after you are done, the root is going to have a higher rank. Okay, so that's what happens. So we make D the root, and now D has a rank of 2. Okay, and well, you keep doing this, and now if you try to take the union of these two sets, then you'll see that the one on the right has a rank of 1, the one on the left has a rank of 2. Therefore, you're going to make the right set the child of the left one. Okay, and as a result, you get this, and again, because the rank of this one is less, the rank of this one doesn't increase. Okay, so now let's look at the complexity. Okay, so what have we done in terms of complexity? Obviously, we didn't change either find or make set. They haven't changed at all. Right? We didn't change the algorithm. Okay, we just changed union, and relatively modest change. Right? We just said, okay, I'm going to make one more check in the body of union. So I didn't really increase the cost of union either. Right? So the only hope is that I somehow, in doing this, I reduce the cost of find. Right? So what did I do to the cost of find?
So it will be O of 1.
How can find become O of 1?
Because for each node we are just maintaining one representative node. So we of the tree.
No, but see, find is always you're given some arbitrary element. So for instance, right? So you're going to be asked find B, right? So find B has to still follow the path. So what is it?
So it will be O of log.
Right. So it's going to be log n. right? So it's going to be log n is going to be its complexity. Okay, so so hopefully that's what we have done. We have taken something which had a worst case complexity of order of n and turned it into order of log n. Okay, so let's. So we know that when we do n operations, the size of the set could be larger than order of n, and because of the way we do this union by rank, so we can say that each increase in rank can occur only after doubling the elements in the set, right? So that's what we are doing. We are saying that only when you put two sets together that have the same rank, then only the rank increases, right? Which means that you are doubling the number of elements, because rank 2 has this many elements and rank 2 has this many elements. So each time you go to this is rank 2. And then when you go from rank 2 to rank 3, you at least have two rank 1, rank 2 child. So as a result, you can say that you can show that each time your rank increases, or again the rank. Remember, at this point, rank is simply the length of the path from the root to the leaf. Okay. So again. We are not necessarily, you should think that this causes the trees to be, really balanced, because you can easily construct a sequence of operations where, you can have, these things going on the side, but you can still prove that in fact what happens is that each time you do the union by rank, each time the rank goes up, you are at least doubling the number of elements, and as a result, the rank can. Once you say that the rank, every time the rank increases, you increase the number of elements by a factor of 2. That means the maximum number of elements that's going to be in the set is n. Therefore, the rank can never become more than log n. Okay. So once the rank can become no more than log n, because rank represents the longest root to leaf path, tells you that find can also be no more expensive than O of log n. Okay? So, question, is this a tight bond, or are we making approximations? Can we construct examples where it does take O of log n time? Can we construct a sequence of O of n operations, right, where using this improved algorithm, the average cost per operation is O of log n? It's not complicated. Once you know that it's not complicated, it's easy to answer. So we know that, if you have, you can easily construct a sequence of union operations so that you construct a tree of size log n, right? That doesn't seem particularly hard, right? And once you construct a tree of log n size, log n height, then all you need to do is to, invoke find on the leaves n times, right? So now again you have two n operations. The second n operations take n log n time total. So obviously when you take the average, it's going to be order of log n operations, log n steps per operation, right? So we have two n operations. The total cost is in the range of n log n. Therefore, average cost per operation is log n. Okay, so it is actually a tight bound. Okay, so now what we're going to do is we're going to try to improve this further. But before we do that, there's a slight change we're going to make. What we're going to do is see in the previous algorithms we did this find implicitly within the union, right? So we called the union on after calling a find. Okay, so from now on, we don't want to do this, hide find inside union, right? So we will just pull it out, and we'll say that from now on, if you want to do union, you only have to give the roots. Okay, if you say give a non-root element, and union doesn't work on those. Okay, so that way from now on, we won't have finds hidden inside unions. Okay, so it just makes it more explicit for the purposes of doing our analysis. Okay. Of course, when you move the finds out of the union, then originally you might have 2n operations. Well, now that has increased, right? Let's say you have n unions and n finds. Now the n unions will contribute additional 2n finds, so you end up, instead of having 2n operations at the beginning, now you have 4n operations. But still constant factor, so for order purposes, we are not going to, it's not different, so we'll just say that all the finds are outside. Okay, so let's see what we can do. So we said find had a cost of order of n potentially, and we reduced that by reducing the height, right, to log n. So now why not go all the way and try to reduce the tree to just height 1, right? Doesn't seem, remember, this is not a forward tree. In a forward tree, there are costs to having a huge fan out, right? So if the root has 200,000 children, well, there is, it's not very easy to represent that. There are, costs to doing that. Whereas if you have an inverted tree, you have 100,000 pointers pointing to the same root. There is nothing, bad about that, right? So therefore, inverted trees can actually be of height 1. Okay, so that begs the question: can we just do that? Is there a way to do this in such a way that the height is always 1, and therefore find will always finish in one step? Well, the trouble is, of course, unions become difficult, right? Because if you have to take union of two sets, well, there are n children of the root in one set and m children of the root in the other set. Now you have to take all these m children and point them so that they point to the root of the new one, right? So unions become expensive. But before that, even to do this efficiently, we need to have some way of accessing the elements of the set given the root, right? So far, we just have an inverted tree. So if you are given the root of a set and ask what are the elements of the set, there is no way you can find them, right? So far, you can't even find them. So in order to do this, you certainly need to do that because you need to find all the elements and update their path. So in order to do that, you have what are called threaded trees, okay? So you have the root, which is A. Now all the elements are accessible from the root, and the way you do that is by just making them a linked list, okay? So this is called a threaded tree because it's like a thread going through all the leaves. Okay, so now with threaded trees, if you want to do the union, then what you can do is you can say, well, I'm going to make P, I want to take the union of A and P, and let's say we have just decided that the root is going to be A. Now what we need to do is we need to basically take this one, right, and we need to make this link go here, right? Or actually not here. Actually, the link from here should go to P, and P should become P should be linked to Q and R just the way it is. Okay. So there isn't a lot of the thread pointers don't have to be updated. That's not a big problem because the thread just gets appended, right? Or prepended here, right? So we have this QR chain that's being prepended to the existing chain of BCD. But you have the other cost, which is to take the parent pointers, you have to update the parent pointers of Q and R so that they point now to A. Okay, so that is the expensive part in this union. Okay, so you can see that if you do this naively, then the cost of union becomes quite high. Okay, because you can. So if you just do this naively, let's say you have n unions, okay, and you do this naively, what is the worst case complexity for n unions? So how can we think of the worst case? What would be the worst case?
We are adding the set which is larger element to the smaller set.
Well, we are not doing that. That's why I'm saying we are 9, right? If you're 9, then what are we going to do? We just have to construct the worst case possibility, right? Which means that we keep unioning a smaller set with a larger set, but we stupidly update the pointers for the larger set, right? And if we do that, then what is the worst case we can get?
O of n where n is the number of
So what happened? Yeah, go ahead.
O of n where n is the number of total elements in the larger
Correct.
set.
So if you have a total n operations, right? So then what can we do? What would be the worst case? So what we can do is we can cause a sequence of operations where you have a set with one element, right? That is union with another set with one element, right? So 1 plus 1, you have 2, right? And then you add another element to this set with 2 elements, except that instead of updating the parent pointer for the one element, you update the parent pointers for the 2 elements, right? So you end up unioning a set with 2 elements with 1, and you have 3 elements, but you also spend 3 units of cost, right? So if you keep following this chain, you end up with a sequence, 1 plus 2 plus 3 plus up to n, which means that you have n square is the total number of parent pointer updates you do, while ultimately you end up with a set that has n elements. Okay, so if you do this naively, then just the unions can cost you order n per operation. But of course, we can do the same trick. We can use the, let's let's only update the parent pointers of the smaller set. Okay, and now if you do this, then what is the cost? Order 1. Why would it be order 1? It is definitely less, that's correct. But why would it be order 1? So the one argument that you can make is that each time I update a parent pointer for an element, it's going to be in a set that is at least twice as large, right? Because let's say I have a set with k elements, and I have another set with l elements, and I'm taking the union, right? So then what I'm going to do is, let's say if k is less than l, then I'm going to take all the elements of k and put it into the set. So I'm going to update So we have updated k pointers. Okay, so we update k pointers, right? But now these elements now find themselves in a set of size k plus L, which is greater than or equal to 2k. Right? So the argument is that each time you update a parent pointer, that element is now going to be in a set that's at least twice as large as before. Right? So what that means is that I cannot be doing these parent updates too often, because by the time I do this parent update log n times, then I would already be in a set consisting of n elements. Right? And if I do n operations, we know that I can only construct a set of size n, and therefore, if I do this, use this trick of updating the parent pointer to the smaller set, or rather merging the smaller set with the larger set, if I do that, then I will always be able to show that the cost is log n, right? And notice that this is not a particular, this is true even with any kind of set, right? If you represent a set using a linked list, right? Now, this kind of set doesn't have to be disjoint, right? So you can have linked list representation of sets of any kind, right? So the same element could be in 20 different sets, that's fine, right? Even in those cases, if you do the union intelligently like this, right, then you can still ensure that you get this benefit that the worst case will not occur, and the complex case will in fact be in the range of order n, log n rather than order n. So, okay, so that's the analysis, and basically each time you change the parent pointer, you're going to be in a set that's twice as large, and therefore you can't do this too often. So basically you can do this only log n times. And so any element will have at most its parent updated at most log n times, because by the time that happens, it's already become already belongs to a set of size n, and that's the largest set you can have. So now we have discussed two ways to do this set, right? So one is the first approach that we discussed is what I would call as an eager approach to, the second approach is what I would call as the eager approach for unioning, because when you do the union, you promote all the children to be the children of the root, therefore finds will actually be efficient, right? The original approach is what one might call as a lazy union, right? Where you just make a pointer, and then when you have to do the find, that's when you will do the work of traversing from the element to the root. Okay? So the question is, so obviously if you do the eager approach, eager union, then find is going to be fast, but the union is going to be slow. If you do lazy union, then union has no cost, right, or constant cost, and find becomes, n or log n or whatever, depending upon how you do it, right? And the question is whether somehow you can combine the best of both and end up with good performance for both union and find, okay? And that is what we're going to talk about, and the technique for doing that is called path compression, okay? So path compression means you are basically going to, retain the lazy union. So unions end up costing just O of one time. But path compression, what happens is that each time you do a find, you will promote that set to be the child of the root. Okay, so this way, it's basically a one-time cost of traversing from the child to the root. Okay, and once you have done that, now this element has become the child of the root, and then there's no longer additional cost. But we don't actually just promote the element, but we promote everything that we see along the path. right? So we are at an element, we follow the path from that element to the root. Everything that we see on the path, we just promote it to be the child of the root. Okay? Obviously, we do this because it doesn't cost us anything extra, right? So we have to traverse this path up anyway, and therefore it will be possible for us to do this update. Okay? So that's why if you have x, then you have parent of x and parent of parent of x and all of them, for all of those nodes, we are going to update the parent. Okay? So from now on, we'll still use the information about rank, right? But rank is not necessarily the same as depth. Because rank, if you recall, is right? So rank is updated here. Right? Rank is updated as part of a union, right? But when you do path compression, now you are compressing and you are changing the height of that. You know, if you take a element from the root, from the leaf level and make it go to the root, then the rank of the, okay, so let's just take this example, right? So right now, the rank of this is 2, right? But suppose we do path compression, as a result of which these two elements, you know, become directly the children of that node. Okay, we are not going to update the rank at this point, because you know there's really no need, because the only reason why we are maintaining a rank is to figure out which one should I make the child of which one. Okay, so we are not going to really update the rank. So as a result, over time, rank may end up being larger than the height of that tree. Okay, but don't worry about it. From now on, the term rank refers to what the algorithm has computed and stored on the node. Okay, so that's what we call as rank, and we will analyze using that quantity. Okay, so here's an example. So let's say you start with the set on the left-hand side, and let's say you do a find I. So find I means I is over here. So what are the elements on the path? So you're going to promote I to be the child of the root. So you see that I has become the child of the root. Then I's parent is also going to be promoted, and its parent, well, it can't be promoted anymore because it's already promoted, right? So all we are going to do here is to promote I and F, and you can see that I and F have been promoted. Okay, so this is path compression. Now if you do find K, well, you're going to promote K and G, right? Because once again, E is already there and it can't be promoted, so going to do K and G, and so you end up with this. Okay, so you can see that as you do path compression, you end up with something that becomes quite flat, and this happens pretty quickly, right? But I want you to, realize, keep in mind that finds and unions are happening, they could be happening in any order, right? So just because at this point G is the child of the root doesn't mean it's going to always remain the child of the root, right? Because you might do a union where A becomes the child of something else, right? So the point I'm trying to make is that don't have this impression that if I do a path compression once, if I do a find once on an element, it has already become the child of the root, and all subsequent operations take order one time. That's not true, okay? Because it is true that if you do a find on an element and then there are no unions involving that set, okay, so then you can say, okay, from now on its cost will remain 1, right? But if you keep doing some unions, then after some number of unions, this element G might find itself at a depth of 4, right? and then, okay, so you got to follow 4 pointers to get to the root. Okay, so that means repeated path compressions can in fact happen, and when they do serve a role. Okay, so it's just something to keep in mind, because otherwise some of the analysis we'll talk about now will not make sense. Okay, so now we are getting to the most interesting and the most complicated part of the analysis. So we are going to define, well, this definition is easy. So we're going to define a function called log star x, okay, which basically says how many times can you take a log on this value till when you get before you get to 1. Okay, so let's see what is. It's a little bit maybe it's a bit too abstract. So here's an example that helps you understand. So think of 2 to the power 65536. Okay, so that can be written as 2 to the power 9 5 times. Okay, so when you take log on this, right? If you take the log once, you will get that, right? You'll just get the exponent, right? If you take the log once, then you get that exponent. If you do the log of that, then you get these 3, right? And if you take the log once more, you get these 2. And if you do it once more, you get that 2. And then finally, if you take the log of that 2, you get 1, right? So the point is that if you take, okay, let's write it down, okay? So log of, let's say x is 2 to the power this quantity, right? So log of x is going to be, right? Log just picks out the exponent, right? Okay, so we have 4 2's stacked on top of 1 2, so we just take that out and we get this. So if you do log x, right? So then we'll get 3 2's, right? So again, when we take the log of that, we just pick up that, right? And if you do log, then we'll get 2 to the power 2. So if you do four times, right? Then we'll get 2, and then if you do it 5 times, we'll get 0 or 1 or whatever, right? We'll get 1. If you do it once more, if you take the log, this is just 2 power 1, right? So if you take the log once more, you get 1. So log star of this number is 5, because it says how many times you can keep taking log until you get to 1. Okay? So one thing that you should notice is that this is a function that increases extremely fast, right? So how big is 2 to the power 65536? It's bigger than anything we can represent, right? And as always, size of the universe is a good yardstick, because we think if you need to represent the input, we probably need at least one elementary particle for each bit of information. So if the number of elementary particles in the universe is only 10 to the power 100, well, 2 to the power 65536 is something like 10 to the power 200, 20,000, right? So obviously, this is beyond anything that can ever be processed by anything in the universe as we know, right? So as a result, we can say log star n is like O of 1, because the maximum value it can ever get to is 5, right? So that's the same thing as saying, well, it's like a constant. Okay? So what we will be able to show now is that the amortized cost of n finds, right, it's not quite O of 1, but we'll be able to show that it grows as fast as this log star function. Okay? So which means that the log star function grows very slowly, and the maximum value is 5 for all practical purposes. Any questions? Okay. So now we are ready to do the amortized analysis of path compression. So as we said before, right, this is nothing new. If you do n operations, the rank will never go beyond log n, right? Because the same argument we made before, every time you update, you increment the rank, we at least double the number of elements. Okay. So what we are going to do is we are going to divide up the rank into several ranges. Okay. Some of the ranges, the starting ranges are very small, right? So there's just one element in the first range, there's one element in the second range. So rank 1 is in one group, rank 2 is in another group, and rank 3 to 4 is in another group, rank 5 to 16 is in the fourth group, and 17 to 4, 16 is in another group, and so on. Okay? And then you can see that at the end, these 1, 2, 3, 4, the sixth range is extremely large, right? Which includes every input size that we might ever conceive of, right? And so, again, to see why this is increasing so fast, because the ranges are of the form k to 2 to the power k minus 1, right? So it goes from k to 2 to the power k. So obviously that's going to be a large range. Okay, and of course when k is very small, then the exponent is not, really having much of an effect. So the ranges are small. By the time k becomes reasonably large, like 65536, then it becomes much larger. I guess I should have shown this as 65536. I don't know why I showed this as 2 to the power 16, because it's a little hard to see what's going on. But anyways, it's k to 2 to the power k minus 1. So what we are going to do is we are going to define this function g, and g is basically log star of rank of v. Okay, so it's basically is picking the group to which of these groups that a vertex that a node belongs to, okay, based on its rank. Okay, if the rank is 1, then it's in the first group. If the rank is 2, it's in the second group. If the rank is 15, it's in the fourth group, right? And if the rank is 100,000, then it is in the sixth group. Okay. Now, one observation we're going to make is that once a node becomes a non-root, its rank never changes. Okay? Why? Because remember, the only place where we update rank is when we do the union, right? And then too, right? So what do we update? The new root, its rank is updated, right? Everything else, the rank is not going to be changed. And so the other point that you see is that if a node ever becomes a non-root, right, it will always remain non-root, right? It will never become a root. Because only if you split sets, then a non-root element can become its own set. But we don't have that operation, right? In the disjoint set data structure, it doesn't support a split operation. It only supports unions and finds. So once a node becomes a non-root, it's never going to become a root. And the only time we update rank is when something is a root. So that means that once a node becomes a non-root, its rank is never going to be updated. Okay? So this is going to be useful. It's a simple observation about the way the algorithm works. It's nothing deep about this. It's just the way we wrote the algorithm. It only updates the rank at certain points, and we can see that it's never updated after it becomes a non-root. So the way we're going to do this is we're going to use all the tricks we have talked about for doing amortized analysis. And the way we're going to do this is we're going to give an allowance to the node when it becomes a non-root. Okay? And because it's, this happens only once, so I'm going to give it an allowance only once, and that allowance will be spent to do the finds. Okay? And that's how we are going to do this analysis. And what is the allowance we are going to give? For a node that is in this range, we are going to give this allowance. So basically we are going to give an allowance which is equal to the largest element in that group. Okay? You'll see later on why we are doing that. Okay? And but this is what we are going to give. Okay? Now, what we need to do is we need to do two things. One is we need to count up the allowances that we give to various nodes and make sure that it is not too large, right? Because what are we trying to do? We are trying to show a total cost, which is something like n log star n, right? That's the cost we are trying to show for n operations. We want to show that it has a cost of n log star n. Okay, so this is what we are trying to show, and we need to make sure that we haven't given so much allowance that the allowance itself exceeds this amount. Okay, so this is not very difficult to show because remember we said that because of the way we are making smaller set the child of the root of the larger set, right? So any set with r nodes, okay, any set with n nodes, right, will have a rank of log n, right? So so if the rank is r, right? So what it means is that your rank r node will have at least 2 to the power r children, right? So once you have a node of rank r, it's going to have at least 2 to the power r children. Okay? Since the total number of children is n, right? So the number of nodes at this height of r has to be at most n by 2 to the power r, right? Because each node that's at a height r is going to have 2 to the power r elements below that, right? So if you have several such elements, then you have to, the number of such elements is limited by the number of leaves, right? The number of leaves is n. So how many nodes at a height r can be there? N divided by 2 to the power r, right? Because each of those height r nodes have 2 to the power r nodes below them. Okay, so we are, remember we gave this allowance 2 to the power k minus 1 for a node in the range k to 2 to the power k minus 1. So if we add up the allowances that we have given, okay, so then we have this number, right? Now, why do we have this number? Okay, so let's write this down. So what we are doing is we are trying to figure out how much allowance we handed out to nodes in one of these ranges, right? So remember we have split this into, at this point, 6 ranges, right? And what we want to do is we want to calculate the allowance that's given to nodes in each range, okay? So consider the range k to 2 to the power k minus 1, right? That means we are talking about nodes with ranks k to 2 to the power k minus 1, okay? So if you have a rank of k, right? So that calculation says if you have a rank of k, then the number of such nodes is n by 2 to the power k, correct? So we have n by 2 to the power k nodes which have rank of k. Then we have n by 2 to the power k plus 1 nodes that are of rank k plus 1, right? And so on. So we have n by 2 to the power k plus 2 nodes of rank k plus 2 and so on. So what is this sum? This is a geometric series, right? So this is going to be nothing but n by 2 to the power k into 1 plus half plus quarter plus and so on, right? So this is nothing but n divided by, so this is nothing but 2, right? So this one ends up being n by 2 to the power, okay, n by 2 to the power k minus 1, right? So this is 2 to the power k multiplied by 2 becomes 2 to the power k minus 1. And the allowance we gave for every node in this range is 2 to the power k minus 1, right? Remember, the allowance we gave for somebody in this range is a higher number. So if you take the total allowance we gave for all the nodes in this range, that is nothing but 2 to the power k minus 1 multiplied by n by 2 to the power k minus 1, which is equal to n, right? So what we have done is we have given a total allowance of n to each of these ranges, okay? So, and how many ranges are there? Log star n ranges are there, right? So the total allowance we have given to all these nodes is n log star n, and that's fine because remember the complexity we are trying to establish is n log star n, and we just need to make sure that we don't give out too much allowance that the n log star n bound won't hold, right? So what we showed just now is that for each of those ranges we gave a total of n as the allowance, and there are log star n ranges, distinct ranges, and therefore the total amount we have handed out is n log star n. Okay? So that's the allowance we have given, right? So now this is the part about calculating allowance. Now we have to think about the cost of the fines and make sure that the cost of fines can be paid out from this allowance. Okay? So the way we do this is, well, what is the cost of a fine? The cost of a fine is the same as the number of parent pointers that are followed, right? So the cost of a fine is simply following the path to the root. Okay? And each pointer followed is going to be updated. Okay? So if we simply count the cost of updating pointers, right, then we would have counted all the costs of all the fines. Correct? Because each fine is going to take all the elements on the path and it's going to update the parents of all of those elements. And as a result, if we simply count the number of parent updates, that is going to be the same as the total cost of fine. Okay? So now, basically what we're going to do is we're going to charge the cost of updating the parent pointer in two different ways. Okay? Case one is your parent has a different G value as yourself. Okay, again, remember G value tells you which of these groups you belong to, right? So if, let's say, your rank is 16, right? Then your parent's rank will be 17, okay? So now your G value is 4, your parent's G value is 5, right? Because basically G tells you which group you belong to. Based on your rank, which group you belong to. Okay, so what we're going to do is, if the parent belongs to a different group, then I'm going to charge this to the find itself. So why do I do that? Because I know that I cannot. Okay, so we'll come to that later. So the point is that if I am updating my parent pointer, right? The number of times I update my parent pointers, I'll find myself pointing to a bigger G, right? That's limited because the number of distinct G values itself is limited, right? So clearly I can say that this step cannot be followed more than log star n times when I do a find. Okay, so I keep following and because the number of distinct G's is so small that the times that I can I'll have a situation where my parent is at a different G is going to be a small number. The other case is, well, I'm going to my parent is in the same group as myself. Well, now I can't charge it to find because I cannot really count this as log star n, because the number of parents I could have that have the same G, that's quite a large number. So what we're going to do is we are going to charge in case where G, the parent of P is in the same class as P itself, then we are going to pay for the cost of that parent update from the allowance that that P already has. Okay, so that is the last thing that we need to do. How do we analyze and make sure that the allowance is enough to pay for it? Okay. Notice that each time I update my parent, right, my parent's rank should be different, should be higher, right? Because basically I'm being promoted, right? Each time I go up by one level, the rank should be higher. So each time pi of P, my parent is updated, my rank is going to increase. So let's consider a series of find operations involving P. Okay? So each time you are going to P has a parent Q0, Q1, Q2 and so on, right? So you start with rank of P and then you make P the child of Q0 and then maybe to Q1 and Q2 and so on, right? So now what happens is that through these updates you want to see how many such updates can happen, right? So what we are trying to do is we're trying to say, okay, suppose what we are trying to count is, okay, again, let's try to recollect what our strategy is. Our strategy is to say the cost of find is going to be counted purely in terms of the number of update operations on the parent pointer, right? And now we are trying to say, let's take a node P and let's count how many times its parent pointer could ever be updated. Okay? And we said, okay, so what we are trying to say here is that each time this update happens, P should find itself be the child of a node with higher rank. So initially when you do a find, P might have become the child of Q0. The next time you do a find, maybe P becomes the child of Q1. And then the next time you call, it becomes a child of Q2 and so on, right? So the point is that each time this happens, the rank has to increase. So this is a strictly increasing sequence. Okay? So what we are going to do is we are going to do this simple calculation that this series, right, is going to be bounded. And how is it going to be bounded? Because we again have this ranks divided up into ranges. So what we are going to do is we are going to say that this series can go from k to 2 to the power k minus 1. Okay? So we're going to say that this series P less than Q0, Q1, Q2, the list of parents that P has, right, it's going to eventually go to, Q0, Q1 up to Qm, right? And the point here is, again, remember, we are trying to account for the cost of parent update when the parent belongs to the same class. Because if it belongs to a different class, then we already said we are going to charge that cost to find itself. So we need to only pay for the parent update in case where the parent belongs to the same G. Okay? So how many such elements are there? The number of such elements that are there is, because the range is k to 2 to the power k minus 1, right? So there are obviously at most 2 to the power k minus 1 elements in this range, correct? So the series from P to Q0, Q1 up to Qm, right? It's going to be at most 2 to the power k minus 1, right? And we already gave this node an allowance of 2 to the power k minus 1. So for each of those parent updates to go from having Q0 as the parent to Q1 as the parent to Q2 as the parent, all the way to Qm plus 1 as the Qm as the parent, right? That's at most 2 to the power k minus 1 parent pointer updates, and we already gave the allowance of 2 to the power k minus 1 to this node. So we can pay for all of these parent updates from the node's allowance. Okay? And once it gets promoted once more, now it goes to Qm plus 1 becomes the parent, but Qm plus 1 has a higher G. So from here on, okay, P's parent is always going to be in a different G class, right? So from now on, the cost of that can be charged to find itself. So from now on, once you have done this 2 to the power k minus 1 promotions, you don't have to do pay for the cost of the promotion anymore from its allowance. So that way you have shown that the allowance is enough to move this through this range, and then finally when it moves to the next range, then you can charge it to find. Okay? So as a result, what we are able to show is that in case 2, the cost of find has been paid from the allowance, and we already said the allowance is total of n log star n, right? In case 1, the cost is charged to find itself, but we said that, okay, the number of parent pointers you can follow in this way is limited. Okay, it's only, there are only log star n number of these things, therefore the number of times you can use case 1 is log star n. So either way, the cost of a find is going to be log star n, right? So what we have said is that the operations, the find operations always cost no more than log star n on the average, because the allowance part is, of course, has to be counted in an amortized fashion, right? Because the allowance is being handed out at the beginning, and unless you take it as an average over n operations, it's a little hard to account for it. So the point is that from an amortized cost perspective, if you do n unions, O of n unions and finds, the total cost is n log star n. Okay? And as we said, log star is essentially like a constant, so you have an algorithm which can perform the disjoint set data structure, basically allows you more or less constant time operation, and that's why it's a very, very useful and very powerful data structure. and obviously we used it in the spanning tree algorithm, and that's a very that's a classic case of use of disjoint set where you try to find out what connected component does this node belong to, right? So to keep track of that, this data structure is very useful. There are many other uses. We'll look at some of them in your homework. Okay, so that's brings us to the end of amortized analysis, where we talked about how by looking at a series of operations and looking at their average cost, we can often end up with a lower average cost per operation, right? And again, remember that lower worst case, right? We're not talking about expected case, we're talking about worst case. And again, it's not just a question of doing the analysis, but using the analysis to guide the algorithm design so that you can tune the algorithm in such a way that you get good performance.